titanium may be Earth's most useful transition metal. To make it, workers wear full protective masks. They use toxic chlorine gas and heat near 900 degrees Celsius. The ore is turned into titanium tetrachloride. The process also creates many byproducts. Some are rare earth elements. They occur naturally in the ore. If you ask me, which metal serves both civilian and military industry? The answer is element 22. Titanium is hard to beat. This is the Surskoye mine on Russia's Kola Peninsula. It is part of the Murmansk Arctic mining region. The ore is rich in titanium minerals, mainly titanomagnetite and ilmenite, with some magnetite, clay, and rare earths. All of it comes from this deposit. After mining, the ore goes to a nearby plant. There, a ball mill takes over. It grinds the ore to fine powder. At first, the powder looks dark and ordinary. Its titanium content is still low, so the plant sends it to a chlorinator, using air pressure to feed it in. The unit handles about 800 kilograms per hour. This creates an intermediate refining product. This differs from blast furnaces, used for iron. After the chlorinator runs for a while, workers insert a long iron canister into the chamber. It checks the hot chlorination reaction and keeps the process on target. Hot chlorine gas is extremely dangerous, so everyone nearby wears protective gear. Next, workers hammer open the upper vent. What comes out of the canister is crude titanium tetrachloride. Still 780 degrees Celsius. Each pot holds about 800 kilograms. That single container is roughly 1 hour of output. Why pour out the crude material? Because it contains more than titanium. It may carry calcium, magnesium, lanthanum, and more. When processing titanium-bearing sand, workers do not get only titanium. Heavy mineral residues come out as well. Looks like ceramics, but one difference is critical. The oily, radioactive sludge cannot be dumped. Workers use special pump trucks for isolated disposal. During carbonate treatment, this Russian plant finds another source of value. It can recover rare earth carbonate. Outside major sources like China's bastnasite deposits, which produce high-purity rare earths. Titanium ore can also hold recoverable rare earths. The material is packed into white bags and shipped overseas. That means export revenue. Rare earths are vital in electronics and aerospace. Advanced manufacturers know their value. Now you may wonder, how do they get pure titanium? That comes next. How does this become usable metal? The answer is the Kroll process. To make sponge titanium, magnesium is needed, for example. The liquid flowing in is titanium tetrachloride. It is denser than molten magnesium. So when it enters, it sinks to the reactor bottom. Workers then insert a long iron rod into the reactor. This lets them monitor reduction. As sponge titanium begins forming, look closely. Focus on this rod. When droplets appear, it tells operators it works. Next, workers keep adding titanium tetrachloride. At least 5 batches may be needed. Once reduction is complete, the reacted material settles near the bottom, while titanium stays inside. Now look at what is left. This is not finished metal, and it is no longer liquid tetrachloride. By this point, the material has solidified inside the reactor. It cannot simply be poured out. This is called primary separation. So is there another step?
Yes.
The second step is deep separation, vacuum distillation. At this stage, the container still holds leftovers. and so the vessel goes into a heated furnace. The system is pulled into high vacuum. In this distillation environment, residual magnesium evaporates because magnesium boils at a lower temperature. As impurities are removed, the titanium mass becomes solid and stable. Here's the simple version. Titanium tetrachloride reacts with magnesium. Vacuum separation removes the leftovers, and sponge titanium is obtained. It sounds like a simple two-step process. In real production, it is much harder. For example, after sponge titanium forms, how do workers remove it from the reactor? First, they load the vessel into handling equipment. Then they rotate it 360 degrees. That moves the sponge titanium from the bottom to the other side. After that, it cools to room temperature. Only then can workers remove it. This is the famous sponge titanium. It is the key step between ore and pure metal. Why only an intermediate product? Because sponge titanium is full of gaps. Its structure is uneven. Most importantly, it cannot be used directly for finished parts. It must be crushed first. Then it is formed into an electrode. After that, vacuum arc melting turns it into true titanium metal. If everything before was preparation, this next stage is the heart of refining. Worldwide, only China, the US, Russia, and Japan have full refining technology. Even Europe lacks the complete start-to-finish process. Here is sponge titanium after first crushing. Workers sort it by hand along the conveyor. The granules must stay uniform in size. It may look old-fashioned, but in this industry, reliability matters. So what are they removing? To be precise, they pick out irregular sponge pieces. If these pieces stay in the batch, the pressing step may fail.
Exactly.
Next, containers of crushed sponge titanium move forward to a massive hydraulic press. Once pressed into a rough form, it looks like a long billet. Actually, in the industry, it is a consumable electrode. Now it gets interesting. Compared with ordinary steelmaking furnaces, the vacuum arc furnace used here gives operators tighter control. Look at the electrode, rough, pitted, and uneven. It does not look impressive yet. To make it denser, cleaner, and stronger, workers move it into a large vacuum. Arc furnace inside. The electrode is positioned for processing. In this vacuum arc furnace, the pressed electrode acts as the negative pole, while the crucible, or crystallizer, serves as the positive pole. The electric arc creates extreme heat, enough to melt granular titanium into a clean, refined ingot with a smooth, dense structure. Its strength and pressure resistance increase sharply. For major applications, aerospace is one of the biggest. Take this unusual metal piece, for example. It is an aerospace component. Even after smelting is complete, the factory's real challenge just begins. First, understand this about titanium. It is not like iron. Iron is much easier to handle. Many tools cut it with little trouble. Pure titanium is different. It grabs and sticks during machining, like tough, stubborn clay. Without serious industrial expertise, it is very difficult to machine aerospace parts to the required precision, beyond aircraft parts. Titanium can also be alloyed into titanium alloy tubing. Titanium alloys handle extreme heat and cold well. Because of these advantages, titanium plays a major role in medicine, where few metals can replace it. Take this skull repair plate, for example. It may look like simple metal mesh, but its market value can be very high. That value is not just the raw metal. It also comes from biocompatibility and corrosion resistance. For that reason, titanium's value in modern industry keeps rising,